In this video, we'll be discussing the process of synthesis. We have discussed how to simulate Verilog designs, and synthesis is the step after that. And we basically want to test out our logic on FPGA, and doing that is called synthesis. So basically, what we want to do is that we have a design available that we have verified in simulation, and we're confident that it will be running, but it has to be transferred onto to an FPGA. We call it burning it on FPGA, and but there are some things to do before that. So basically, FPGA would be in form of some board that we have available. So we'll have to buy some board and try it on that. And that board will be connected to different interfaces depending on the design. We might want to communicate it through a communication link, and maybe we want to sample some data using ADCs. We want to maybe see the status of some things on LEDs, maybe connected to push buttons. This is a poor design, poor diagram for a push button, but anyway. And we want to also might also want to connect it to some expansion connector with pins going out to some other board. So these are pins. If they're looking not looking like pins, that's my fault. So forgive me for my drawing. So basically, what we want to do is we want to assign pins to ports and ask the tool to do the rest. So basically, that's what we do. So, so the tool then synthesizes the Verilog code, translates it, maps it, and plays and route it. All of that is done automatically, and it can optimize for clock and area. We can change a few settings for that, and then we generate a programming file, and that file is actually programmed onto the FPGA. After that, we just connect the programming cable to the FPGA and try it out. So that's the main thing. So how to assign pins to the FPGA? FPGA pins are generally numbered like A1, A2, A3, A4, or A18 to B18 or something like that. And we want to tell the tool that this specific pin needs to be connected to this specific signal in our design. So that is done in a constraint file. Normally in Vivado, it has extension XDC. In earlier variants of Xilinx ISE, it has an extension UCF for user constraint file. XDC probably stands for Xilinx design constraints. So if you're using Altera, then it will be some other name, but then there you will also have some constraint file to for the same purpose. XDC in XDC we can give different kind of constraints, but most common are two type of constraints. One is first one is the constraint that connects a specific pin to our signal name in the top level Verilog code, and that is this constraint. So we what we do is now this constraint is connecting this port named clock to this package pin. So this L16 is the FPGA pin that we want to connect the clock to. So we already need to know somehow that on which pin we're expecting clock. I'll shortly tell how can we know that. So the second type of constraint is a period constraint. So for clock signals, this is for clock signals. So basically, in an XDC file, there are many statements like the first one in which we connect all the signals, and then there are a few statements like this, which basically provide the clock constraint. So this constraint is telling the tool that we have a clock of a period of 8 nanosecond with a waveform that it will remain low for first 4 nanoseconds and it will go high after 4 nanoseconds. So basically 50% of the time duty cycle is such, and this is telling that we need to we are looking for this port named clock on which we are assigning this constraint. So this constraint will help the tool to have a target to be able to synthesize, and so Vivado will try to synthesize it, and if the resultant design that we have made can satisfy this constraint of having of maximum delay of 8 nanoseconds between different clock cycles, then it will tell us that timing has been met. Otherwise, it will tell us that timing has not been met, and it will tell us about by which margin it has not been met. So that's what we want to do. So we'll go back to the design that we covered in the first or second lecture. So we made a counter which was used for increment and decrement, and we wrote Verilog code for that. So now we want to connect it to the FPGA. So basically, we have these inputs, increment and decrement, and output count. We also have clock and reset as input. So these inputs and outputs we want to connect. So right now I have this board named Zybo, which I'll be for which I'll be synthesizing the design, and I want to test out my logic of counter. So first of all, I need to connect things. So I can see that on this board I have four push buttons. So I can connect one of them to reset, another to increment, another to decrement. Clock will be automatically connected, so it's off the shelf board. It already has connections made, so there is a crystal on board from where we derive the clock, and that clock is connected to some FPGA pin that we'll shortly see. And for output, I can see it on maybe LEDs. I have four LEDs, so I can connect the count to those four LEDs. Then I can it would have been better if I could see it on a maybe 7 segment display, but there isn't any, so we can look at it on the LEDs in binary form 0, 1, 2, 3. Anyway, binary is good for logic designers, so we don't mind them. The only problem we have is switch bouncing. So, that whenever we press this switch, these are mechanical switches, and when they get back up, when we release the switch, it also it bounces multiple times. So we get on signal multiple times. The design was expecting that increment will be a single cycle pulse that will be on for one cycle, and decrement will be a single cycle pulse. So if I press the button, it will not only be turned on for a long period of time, so incrementing counter many times, but it will also bounce up and down, and it will be on multiple times. So we want to resolve this. So to resolve this, we can actually have a what we call is a debounce circuit. So basically, I've made a small change in the design. I'll add that debounce circuit in increment and decrement paths. I don't worry about reset, because even if reset bounces, it doesn't matter, because in the end it will just reset the system. But I want to increment and decrement. I want to increment it only once when I push the button, and I only want to decrement it only once when I push the button. So I have made a small circuit that actually is enabled whenever there is a 1 on increment, and for a programmed number of cycles, it doesn't look at the input anymore. It just waits for a while till everything is settled down, and after that it actually increments. So that's how it's handled in our logic. So I'll switch to Vivado and show you how to do that. So in Vivado, if I want to implement it, I'll create a new project. Project. I don't know. It's taking a lot of time for some reason. Okay. So maybe I want to say test the counter, and next I want to make a RTL project, uh, and I don't want to add any files at this moment, or not any constraints. I'll add them later. Uh, Next thing is that I want to select the part number. So in Vivado we can actually select the board as well. So I'll do that. I will just type in Zybo here, and this is the board, and just finish. Okay, it will automatically create the project. I've created it on desktop, and since I have selected the board, so Xilinx already knows this board, and it will uh, know the exact part number of the FPGA, and it will select it automatically. Next thing is that I want to add my sources. So first of all, I want to add my counter files. So uh, okay, so I'll just create a design file, and I'll say is a create file. It's saying Verilog, so I want to write it Verilog. So counter and finish. Okay, it's asking me whether I want to add some input and outputs, but I generally prefer writing it in code because it takes lesser time. So it will just create it. So that's our counter.p that uh, say. So it's an empty module. If I had added some inputs or outputs, it would have been here. Now I want to copy paste my code. So I think here it is. Hopefully. Okay. So this is the same code. Just I have added this module of debounce at start of it, not in the start uh, with increment and decrement. So I'll just remove it and paste it. So this is my code. So I also need to have this module here, so I can either add this file. So I can add the sources as well, but I'm just for the person who is writing for the first time, he'll probably would want to write code. So I did a new file. Otherwise, if we already have the source files, we can add those. So I have pasted the module of debounce here as well. So here we have both things ready. So this is the first thing that we already know how to add files to a project, but the main thing is that we also need to connect the pins in an XDC file. So where first of all, where to get that XDC file? So whatever board you have bought, it normally the vendor gives you a master XDC file. So if I search it on Google, here is the page for Zybo, and here you can see master XDC file. If I click it, it will open this GitHub page where they have XDC files for all the boards from Digilent, and that is the vendor. I've already downloaded it. You can download zip file, and I've extracted it. So here I have those XDC files. So here if I open this master XDC, this is the file. So if you can read here, it says that uncomment the lines corresponding to the use pins. So whatever I want to connect. So here we were discussing that we want to connect clock, reset, increment, decrement, and count with these uh, pins. So I can see that here is the first signal is the clock signal. So I can copy it, and now I can add source, but this time I'll uh, select add or create constraints, and I can say that create file. You can see that it's saying XTC, so I can name it counter and finish. So here in the constraints we have now one file, and I can open it up, and I can copy paste the clock signal. So since I've copied it from Zybo master XDC, so we already know that this pin number is correct, and it has a period of 125 megahertz. 8 nanoseconds translate to 125 megahertz. So if you want to verify it, you can also go to the vendor's user manual that it has provided. For example, here is the reference manual of a Zybo board, and it tells us that it has external 125 megahertz clock at pin L16. So we can see that the same pin is connected in the master X. We see that we copy pasted. Next, we want push buttons. So here are the push buttons. So we want three of them for reset, increment, and decrement. So I'll just copy it and paste it. I personally prefer using Notepad++, but this editor is also reasonably okay. Uh, and I don't want to connect it to the port name button. I want to connect it to whatever I have used in the design. So in my design, I have used reset. It's better to copy it and paste it so that there is no spelling mistake. Uh, so I want to connect the next one to increment, button 1 to increment, and I want to connect pin 2 to decrement. So three buttons are connected. We are not using the fourth one because clock is already connected, so we we only need three other inputs. And also I want to connect the output to the LEDs. So uh, I have to copy, these are the four LEDs right in front of us, so we just copy it here and paste it here. Okay. And just delete and copy the count. Okay, maybe I can. So just copy count here, then here, then here, then here, and that's it. That's my design ready to be synthesized. So now next we ask the tool to synthesize, implement, and generate programming file. So if I click generate programming file, it will do all the steps. First step is synthesis, next is implement. Synthesis kind of synthesizes it without actually mapping it to the exact FPGA architecture. It just uses the building blocks of the FPGA but not map it to exact locations. Implement design basically maps it to exact locations and try different things out to try to meet timing. Uh, and then we finally have this generate bitstream actually generate the FPGA programming file that we normally call bit file. So I'll just run it. It says that there is no implementation available. Do you want to run it? Yes, I want to run it. And now it will take some time, so I'll just pause the video. Okay, so I got this error here while implement designing. So I'll just take a look into it. Oh, okay, it is saying that I should have used count. Count is an array, so I can use it directly. So last one was 3, so I'll just have to do it again. I'll paste count again. Count 0, count 1, 2, count 3. Okay, so I'll save it and again run it and pause the video again. Okay, so the synthesis is complete now. I can either open design or view reports. I'll open view reports. One thing to make sure when your design is done is to look at the timing report of the design. So, for example, here it is, and I'll open it. You can. The important thing is to make sure the timing has been met. So this line is the key. All user specified timing constraints are met. So basically we just gave one timing constraint. It's a small design and we were expecting it to be met, but make it a habit to always check the timing. If it is not met, then you should go and see the timing analyzer and what happens. So once you're done with it, then you need to connect your board. So you've seen the board diagram that I've already shown. Maybe this is my board. It has a programming cable normal that connects to the USB port. From here, this is the programming port. I will connect it to. I've already connected it to my USB port of this laptop, and now what I need to do is I just need to program it. So for programming it, we go to hardware manager and we open target, auto connect. We had another project open if it doesn't make any issue of that. So I want to program the device. It's already selected the device that we want to program, and it has already selected the bit file. So the whole output of this synthesis process is a file with extension .bit. So we call it a bit stream file that actually programs the FPGA. It has the same name of that of project of the top level file of the project. So I had counter.p, so it's generated counter.bit, and I'll just program it. So when we program it, there is a done LED on the FPGA that will start to glow. And now I'll move to my mobile camera to show you what we can see there. Okay, so I have connected this FPGA board and programmed it. So it's already reset, so you don't see any LEDs. Now if I increment it, you can see that one LED is on. So this is 0001, and then I increment it twice. I get 10, then again 113, then 1004, 1015, 1106, and meanwhile if I reset it again, I get 0, and again I can increment 1, 2, 3, 4, 5, 6, and I can also decrement it using third button from 6 to 5, and 4, then 3, then 2, 1, and 0. And obviously if I decrement beyond 0, I get -1. It's all ones, so if you understand 2's complement numbers, it's -1. Okay, so one last thing that is about the specific board is that when I was creating the project in Vivado, I was able to select this board, but if you try it yourself, you might not see Zybo board there. That's because the standard Xilinx boards are already there, but some of the Digilent boards are not by default there. So to be able to see them there, you need to copy board files. So if you go down the page, there is a link for installing Vivado and Digilent board files. So this is the page where you can from where you can follow it step by step. You can download the board file, and then you'll have to go to a specific directory in the Vivado installation and copy the board files there, and it will automatically pick those up. So that's one thing that's specific to this board. If you're using some other board, it might already be there by default. If it's not there, then you might have to download the board files and copy them there.